Hi, in the previous video I explained the physics of central force motion and developed two coupled differential equations governing the motion under a gravitational force. Today we will delve straight into the Python code for simulation and animation. So without wasting any more time, let's jump into the computer screen. So to begin with, we have to import the scientific computing Python libraries which will help us. So you need to install them using the pip install command from the command prompt in case you are using Windows, or if you are using Linux then you have to do the same thing in the Linux terminal. So I assume that you have already installed these modules. I will quickly introduce them to you. So at first we need to import NumPy. NumPy is a module which is used to create arrays for storing the values that will be plotted. The second one is the main module for this program, that is from scipy.integrate import solve IVP, where IVP stands for initial value problem. It is a function available in the module scipy.integrate, which is a differential equation solver. Next we have the famous matplotlib.pyplot as PLT. We are importing that. So it provides the class func animation in this case, which allows us to animate the motion of the particle. So matplotlib is basically a plotting module, and under matplotlib we are also importing this submodule known as func animation. And for very small tasks we are also importing the math module, which provides various mathematical functions which in this code are used mainly for beautifying the plot. So apart from these libraries, we also need to install an external application named FFmpeg for saving the animations. So as we are in Windows, we need to go to the official website of FFmpeg, that is this one, ffmpeg.org/download.html, and we need to go to the Windows icon. We need to click the Windows icon, and here are two options. So these are the two build providers. The version which I have installed on this system is from gyan.dev. So we click on it. You are redirected into this website, which is the gyan.dev website. If you scroll down, you will get to the release builds, and in my device I have this version installed, this version FFmpeg 7.1.1 full build. This version I have installed, but now I think they have also released few latest versions, so you can check that out. But the version which I have installed is this one. So once you click on it, you will get a .zip file downloaded in your downloads folder, and you will then extract the files. One more thing which you have to do is that you have to go to the system environment variables. You need to type edit the system environment variables, go to this menu over here. So these are the environment variables, and under system variables you can find this path. Double click on it, and these are the programs which are added to the path. See, you can find this one here. So you have to add this manually. You have to install the .zip file, go to the bin folder, copy the path of that particular directory and paste it here, and save this particular path. So once you have done it, if you want to check whether it's working or not, you have to just type ffmpeg hyphen version, and if you press enter, then you will get this. This is just the it is giving the version of ffmpeg installed, and if this shows, ffmpeg is downloaded properly in your system. So after declaring all the Python modules, the next thing that we will do is that we want to actually show a few messages about this program to the user. So the first thing that we will show is this. I will just print this statement. This program will show the motion of planets around the source of gravitational force. So I am basically describing the purpose of this Python file and uh, what Python will actually do in this program. The next line which I am going to print is this. At the origin 0, 0, mass capital M is situated, which will act as the center of force around which another mass M will move gravitationally. That's exactly what we are trying to do. And the last line is the trajectory of the moving mass will be calculated using Newton's law of universal gravitation. Now it's the time to ask the user for all the initial information about the two particles. So first I would actually like to present the user with a default set of initial conditions which the user might select, or if the user wants to actually use his or her own set of initial conditions, he can do that. I will write this code. So I am declaring a empty string I, which the function of which will be clear in just a moment, and there is a while loop. So while I not in y comma n. So these two are the user inputs, yes and no. What's the question then? The question is given here. Do you want to use the default set of initial conditions? The answer is yes or no. If the user types y in the keyboard, that character y will be stored in the string I, and this set of initial conditions will be fed into Python, right? Okay, so the first information is the mass at the center, which is capital M, that is 1000. Mass of the particle, which is small m, that is taken as 1. Now gravitational constant is equal to 1. Now you will ask me that wait, gravitational constant is definitely not equal to 1. It is equal to 6.67 times 10 to the minus 11 Newton meter square per kg squared, right? So knowingly why I am just writing the value of capital G equal to 1. The thing is, we can definitely use a different set of units so that the value of gravitational constant becomes equal to 1. This is something we also do in, for example, special relativity, where we change the units in such a way so that the speed of light in vacuum becomes equal to 1 instead of its actual value in meters per second. So I can definitely do this. There is no harm in setting the value of capital G equal to 1. So initial x position is 5, initial y position is 5. So these two are the Cartesian coordinates of the initial position, x and y. Initial speed is 8, and initial speed's angle with the x-axis is 180 degrees. So the initial speed is given and the initial speed's angle, so the orientation of the initial velocity is also given in terms of the angle, that is 180 degrees. And this is the start time of the simulation, which is t equal to 0, and the end time of the simulation, that is t equal to 3 seconds or 3 units of time, because I should not use seconds because gravitational constant is equal to 1. I have to remember that, right? And this is the prompt. Press yes, press y for yes and n for no. If the user presses y, so I have to actually give if I double equal to y colon, and then these initial conditions will be actually fed into Python. So these are the actual declaration of capital M, small m, g, x naught, y naught. So these are the initial x position, y position, initial speed is v naught, alpha 0 is the initial velocity's angle with the x-axis, ts is start time, te is end time, and this is actually alpha 0 is equal to np dot pi by 180 into alpha 0, which is basically converting alpha 0 to radians. So this is in degrees, 180 degrees, 180 degrees I have chosen, but I have to convert it to radians. If I do not do that, then the trigonometric functions in NumPy library will not work correctly because they only work with angles in radians, right? So I converted this alpha, multiplying it with pi by over 180 to make it in radians. That's it. And this while loop is acting like the do while loop, but since this is not C, C++ or Java, this is Python. Python doesn't have a do while loop. So I had no choice but to use the while loop as a sense of the do while loop. We should not forget that throughout this calculation or throughout this program, we are sticking to the plane polar coordinate system. As our initial position x0 and y0 are in Cartesian coordinate system, we must convert them into the polar coordinates r and theta. So from this diagram, you can understand that the position vector r is simply the hypotenuse of a triangle having the other two sides x0 and y0. So r0 will be simply the square root of x0 squared plus y0 squared. The other coordinate, which is theta, and here we will call it theta naught. To find it, we just need to evaluate the tangent of theta. From the diagram you can say it is y naught by x naught. So the angle theta will be simply the tan inverse or the arctangent of y naught over x naught. To evaluate the square root, or in other words the size of the hypotenuse, NumPy provides a ready-made function called np.hypot, where hypot stands for hypotenuse, and for calculating the arctan or tan inverse, NumPy also has another function called np.arctan2, which will evaluate the arctangent for us. So here we will declare r0 equals np dot hypot x0 comma y0 for the hypotenuse, and instead of theta we will give O 0 because O somewhat looks like theta is equal to np dot arc tan 2 y0 comma x0. Now what will happen if the user wants to input his or her own set of initial conditions? So for that we need to type elif I double equals to no, n for no, right? Under this if block we will be actually coding the part of the user inputs. So first we need to ask the user about the choice of gravitational constant g. So let us put a comments here. Now again I want to start a while loop, and inside the while loop I would actually ask a question to the user. So while true, c equal to input, do you want to use universal gravitational constant, which is 6.67 times 10 to the minus 11 as g? Using the actual value of gravitational constant will result in a very slow simulation, which is true actually, because gravity is a very weak force and it will take a very long time for the motion to actually make sense. And I am asking the user yes or no. Now if the user types yes, so if c equal to y, then I would just declare the value of gravitational constant and I will break the loop. Now if the user says no, then I would actually take the value of g from the user. So I would write float input like that. So this input function will actually allow the user to type through the keyboard his or her own value of gravitational constant, and when the user presses enter, that value will be stored in the variable g, capital G, and again I will break the loop. Now what is the purpose of the loop? Again I am using a while loop because I don't have the do while loop. So else I would just print a default message. So if user types anything apart from y or n, then this else statement will work and wrong choice try again will be printed on the output window. So after the gravitational constant g, we will now enter the value of the two masses. So the first mass, capital M, now the other mass, small m. After the masses, the user is going to enter the time range of simulation. So we will ask for it. We will store the start time in variable ts and the end time in variable te. For solving the two coupled differential equations which I derived in the previous video, we need to provide Python with the initial position and velocity of mass m. So we shall print, now it's time to enter the initial conditions. Starting with the initial position, we would ask the user whether he or she wants to use Cartesian or polar coordinates. So just like before, we need a do while type while loop. We want the user to input capital C for Cartesian coordinates or capital P for polar coordinates. Now for Cartesian, we would just take x0 and y0 as inputs and use the hypot and arctan2 functions to convert them into polar coordinates. If the user chooses polar, we would simply take r0 and theta0 as inputs, and here theta0 is taken as o0 and convert the angle theta into radians. Just like before, there will be a default statement for wrong input. We will do a similar thing for the initial velocity as well. Choice of inputting in Cartesian components or speed and angle will be given to the user. Again, we start the while loop and store the Cartesian components of initial velocity in variables vx0 and vy0. Then we calculate the initial speed v0 using the hypot function and the speed's angle with the x-axis alpha 0 using the arctan2 function. For if the user wants to provide with the initial speed and angle directly, we would store the speed in variable v0 and the angle in alpha 0, followed by the conversion of alpha 0 to radians. Just like before, there will be an else block containing the default message for wrong input. As discussed previously, we are converting a two-body problem to an equivalent one-body problem. So we must calculate the reduced mass using the masses of the two particles, capital M and small m. So mu is equal to 1 over 1 by capital M plus 1 by small m. For solving differential equations using scipy.integrate submodules solve IVP function, we need to follow a specific syntax. For clarity, I will first write down two comment lines saying that variable r indicates the radial coordinate and variable o indicates the angular coordinate theta. The first step is to define a function. Here the name of it is capital S. It has t and z as arguments, where t is time and z is a list of quantities. In the second step, I will declare all the variables r, o, u and v and equate them with z. Recall that u and v were the two variable substitutions we made in the last video. The third step includes the declaration of the differential equations. The first two being the two variable substitutions dr dt equals u and d theta dt or do dt equals v. The third and the fourth are the two coupled differential equations which we derived after applying Newton's second law. Finally, we return the list of all the quantities dr dt, do dt which is d theta dt, du dt and dv dt. This is the fourth step. Carrying forward the syntax, we will store the start and end times of the simulation in a tuple named t underscore span, followed by a list t underscore eval which contains 2000 time values within the given span of time t span. Next, we need to feed in the initial conditions to SciPy solve IVP. For that, the first thing which we have to do is to find out the polar components of the initial velocity of the particle. Now, you might be wondering, we did actually take the initial speed and its angle with the x-axis as input, right? However, they are not the polar components. For understanding this crucial concept, look at this diagram. v0 is the initial speed and alpha 0 is its angle with the x-axis. Theta 0, on the other hand, is the angular coordinate of the initial position. It is clear that v0 and alpha 0 are not even close to being the polar components of the initial velocity. We actually need to resolve the v0 vector into two components, one along the r cap direction, another along the theta cap direction. The component of v0 along r cap is vr0 equals v0 cos theta naught minus alpha naught, and the component of v naught along theta cap is v theta 0 equals minus v naught sine theta naught minus alpha naught. The minus sign comes as the angular component is opposite to the direction of theta cap. After this step, we need to simply type in the expressions for Vr0 and V theta 0. Then we need to give the list of initial conditions Z0. The initial conditions are to be declared in the same order as it was declared within the function capital S. So, R followed by theta, followed by U, and finally V. Remember the two variable substitutions? As U is equal to R dot, which is the radial component of velocity, we plug in Vr0. But V, which equals to theta dot, is not the angular component of velocity. So to convert V theta 0, which is the angular component, to theta dot, we need to divide it by R0, as the angular component of V is equal to R times theta dot. After that, we need to simply invoke the solve underscore IVP function, providing it with necessary information, which include the function capital S, the time underscore span tuple, the list of initial conditions Z0, the time array T eval, and the name of the numerical method, which is radau. I actually tried to use RK45, but it did not give proper results. You can find information about radau method in the official SciPy's website. The solutions we need are the array of r values, which is stored in variable r, and the array of theta values is stored in variable theta. So 50% of our work is done. The back end of the program is ready. We only have to code the front end. As I am fond of the dark theme, I would like to change the background of the matplotlib interface to a dark background. The next line introduces a figure object and an axis object with polar projection. The size of the canvas is set to square figure. The subplot underscore kw equals projection colon polar tells matplotlib to use polar coordinates instead of Cartesian. Ax.plot plots the trajectory of the moving mass small m, so it draws r as a function of theta. The title of the plot is set to motion under gravity with proper placement. The circular grid system is enabled with gray color. The ax.legend function puts the legend on the plot. As the polar plot by default does not come with the Cartesian axis, I drew them manually using the annotate function. Both the axes have lengths equal to the maximum value of array r, which means the maximum radial distance the particle goes from the origin. The axes have arrowheads on both sides, white in color, and has line width equal to 1. Next, we will label the axis as x and y with ax.text function. The following codes are completely used for matplotlib beautification and do not require detailed explanation. I have written Cartesian style axis numbers. If the radial distance is large, here larger than 25 units, the consecutive numbers will come so close to each other that they will overlap. So to prevent clutter, the numbers will show only when the maximum radial distance is below 25 units. The moving mass small m will be represented by a marker with marker size equal to 8, which is drawn using the ax.plot function. Just for styling the mass capital M at the center, I have created a stylized sun which have a filled circular disk that constitutes the sun's body and a wavy outer boundary to suggest glowing solar flames. You may skip this part of the code as it is totally optional. The update function is the function behind all the animation stuff. It will be called by func animation later. The function has an integer parameter named frame. Each value of the integer corresponds to a time step along the pre-computed arrays theta and r. The marker.set_data line moves the marker associated with mass m along the trajectory. Then the sun's outer glow is also animated, which creates the dynamic effect of it. Finally, the function returns the animated quantities marker and outer_sun. We also mark the starting position of mass m using the plot function and label it as initial position. plt.legend function assures that the legend is visible. The final aspect of the code is to animate the plot, give user the option to save it to disk and display. As we will be asking the user whether he or she wants to save, a while loop will be used like a do while loop which forces valid input. If the user chooses to save, we would ask for iteration increment, which is the number of data points skipped per frame. The frames will be generated using the range function inside func animation. The frames per second FPS value will also be asked. The func animation function is called and all the information like the figure, update function, frames, interval, which is the delay between consecutive frames, are fed into it as parameters. Then the save function does the job of saving the animation in an MP4 file named motion_under_gravity. The writer, which is the external encoder, is FFmpeg, the software we installed long ago. FPS, DPI and bitrate are also provided as parameters. After saving is completed, a status message will be printed. If the user does not want to save the animation, only the iteration increment is asked, followed by the func animation line. After the default else statement, we write plt.show function, which opens the matplotlib animation window and the animation starts to play. And with that, we come to the end of coding. Okay, so I have decided actually to run the program through the command prompt because it would look very nice instead of just running it inside the VS Code environment, right? So I am in that particular directory on which the program was written. So the name of the directory is CFM video, and you can also check if I type dir, which shows all the files and directories inside this particular folder. If I click enter, then you can see that this one is actually my Python file which is present inside this directory, cfmvideo.py. It's written here. Okay, so clear the screen by typing cls, and now we would execute the file or run the file. So I will type python cfm and press tab. Yes, this is the file cfmvideo.py. If I press enter, the file will be executed. So in 3, 2, 1, let's go. As usual, the program is initially showing me a set of information. This program will show the motion of planets around the source of gravitational force at the origin 0, 0, mass capital M is situated, which will act as the center of force around which another mass small m will move gravitationally. The trajectory of the moving mass will be calculated using Newton's law of universal gravitation. That's a very good way to start. After that, it is showing me the default set of initial conditions, that is capital M equal to 1000, small m equal to 1, capital G equal to 1, x naught is equal to 5, y not equal to 5. You know all them, right? Okay. So I think I should first go with the default set of initial conditions. So I will press Y. Do you want to save the animation in your current working directory? Yes, we can do that, but I think not now. I will do the saving. I will show you the saving thing later. So no. Select the iteration increment. There is 5 shown here as an example, but I would like to choose 3. And if I press enter, you can see here it is written animation will not be saved, and voila, what we get here is the beautiful animation of the particle moving under a central force. You can see that Python has solved the equations to reveal the elliptical orbit. The sun is also dynamic, as we have made it, as we have animated it, and the particle is beautifully going round the trajectory. You can also check the trajectory is correct or not, or rather Python has solved it correctly or not. This is the initial position, and if you draw tangent at the initial position, the tangent will be horizontal, indicating that the initial velocity's angle with the x-axis is 180 degrees, and that is exactly what the default condition was. You can see over here, initial speed's angle with the x-axis is 180 degrees. That's why the tangent is horizontal, which proves that Python has solved it correctly. How beautiful it is. Now let's try to actually give few initial conditions instead of choosing the default ones. So I would like to again clear the screen, then python cfmvideo.py, so the command to run the file. Now I will press no. Do you want to use the default set of initial conditions? I would say no. Okay. Do you want to use universal gravitational constant as capital G? Using the actual value of gravitational constant will result in a very slow simulation, so we would not do that. We would say no. Enter your gravitational constant. We would choose G to be equal to, let's say, 2. Okay. Enter the mass at the center, 800 this time. Enter the other mass, 1. Enter the time range of simulation. Okay. So start time is 0 and end time is 3. Very nice. Now it's time to enter the initial conditions. Initial position of mass m. For Cartesian coordinates press C, for polar coordinates press P. So we are going to take the Cartesian ones. So C. Enter the x value. So x value is 5 of initial position, and y value is also 5. Okay. Initial velocity of mass m. For Cartesian components press C, for speed and angle press P. We are going to input the speed and angle, so we would press P. Enter the initial speed. So initial speed is 7 and the angle with the x-axis is 90 degrees. So if you remember from the previous plot or the previous animation, the angle was 180 degrees before, because the tangent drawn at the initial position was horizontal. Hence, by the same logic, here the tangent should be vertical. We'll see that. Do you want to save the animation in your current working directory? Okay, so let's save it this time. So we will type Y. Select the iteration increment. For example, 5. I prefer large increments for quick saving. I would prefer 4. Select FPS, not more than 30 FPS. Saving. And this will take some time, like half a minute or so. So let's wait for it while it renders the animation for us. So it did not take even half a minute for it to complete saving. It is written animation saved successfully with file name motion under gravity.mp4, and here is the plot. So as you can see that we are also getting an elliptical orbit this time, but the ellipse is like a little bit flattened and it has sharp edges. Okay, and you know how to check whether Python has solved it correctly or not? You just need to draw the tangent at the initial position, and if you imagine the tangent here, that is clearly 90 degrees, that is clearly vertical. So that matches with our input because we chose the initial angle to be 90 degrees. If we go to the folder, this is the folder where all the files are there. Here you will find this mp4 file, which is motion under gravity.mp4. If you open it, then you can find it saved. The saving specs will be of course 30 fps because we chose that value. You can also choose 60 fps, but if you do that, then the saving time would definitely increase. So I would like to give another set of initial conditions. So let's clear the screen once again, run the program, press no. So we won't use the actual value of g, so we press no, and our gravitational constant will be equal to 2 once again. Mass at the center is 800. The mass small m is 1. We are again going to give Cartesian coordinates. So c, x position is 30, y position is 5, and speed and angle, so p. Initial speed is 15, final and the theta is 170 degrees. Do you like to save the animation? I don't think so, so no. Selecting the iteration increment, again 4, and here is the beautiful plot that you can see. So when we actually do solve the differential equations analytically, we get the equation of a conic, and we actually do get all the 4 types of conic sections. Those are circle, ellipse, parabola and hyperbola. It actually depends on the total energy of the mass configuration. Here I think we have got a hyperbolic trajectory of the particle. It looks so nice. This brings us to the end of an extraordinary journey of simulating and animating central force motion. I hope you liked this video and learned something. I have thought of uploading more such interesting videos in the future. So till then, enjoy physics and keep smiling.